Okay, so today we're going to begin a new topic, obviously building on our understanding of the geodesic equations, and we are going to actually apply those geodesic equations to the Schwarzschild spacetime. Now, we haven't studied the Schwarzschild spacetime, but we don't really need to for this purpose, because as you already know from the earliest lectures of this series, when I talk about a spacetime, what that literally means is I am going to talk about a metric. When I say I have a space-time, what I mean is I have a metric. And how we get that metric is through the Einstein equation, which is really the second half of this course, where we take the Einstein equation and we find this metric. But we are now going to presume that that's done, and we have a metric that describes the space-time. In particular, it's the Schwarzschild space-time. Now, we could proceed without any further discussion of what this means or what this is, but let's just say that the Schwarzschild spacetime is a spherically symmetric spacetime, and it really represents a non-rotating, spherically symmetric ball of matter and energy, and it's the spacetime surrounding that non-rotating spherical ball of matter or energy. It doesn't include, by the way, the interior of that object. It only includes sort of the exterior of the object, which will be an interesting topic when we discuss how we derived it. And if we ever do the Kerr black hole, then it even becomes more interesting. Okay, so we are going to study the geodesic equations of the Schwarzschild spacetime. Let's begin. As with all our beginnings, we're going to go and begin with the catalog of spacetimes. This is where we're basically using this as our reference. We're going to consider it somewhat canonical. I'll make some minor notation changes. For example, they do not generally use c equals 1, which I find a little annoying for a canonical reference, but I understand why you might not want to do it. You might want to keep it flexible and full generality, and so you want to show where those c's would come in. So we'll make a few adjustments on what we get, but we'll always refer to it as sort of our source material. And in that vein, we will go to section 2.2, which is titled the Schwarzschild spacetime. And in it, you will have all of the details about the Schwarzschild spacetime. Of course, why not? It's a catalog of spacetime. So the Schwarzschild spacetime is the first one anybody ever learns about that isn't just flat Minkowski space, which we've already done. We've already done flat Minkowski space. So what we're looking for is we need the metric, right? We are looking for the metric, because from the metric we will develop the connection, and from the connection we will develop the geodesic equations. So we start with the metric, and there it is. Notice that they don't list the metric elements. They don't say G00 equals minus 1 minus RS over R, right? They don't do that. There's their little c squared, by the way, which we attach to the dt squared, so we'll peel that off. They don't say that. They just establish the line element. They present the line element. Now, the way you're supposed to be smart enough to know that, well, let's see, x0 corresponds to t, and x1 corresponds to r, and theta corresponds to x2, or I should say x2 corresponds to theta, and x3 corresponds to phi. Therefore, this is x0, x0 squared, x1 squared, x2 squared, and x3 squared, right? But of course, it is a bit of a mess to go x0 squared, right? So it is pretty common to get rid of the formalities of the superscripted coordinates and give each coordinate its own name. When you're really digging into one example, you give each coordinate its own name that's suggestive of what it really represents in the simplest coordinate system. And in this case, you're dealing with spherical coordinates, and theta and phi are actually the azimuthal and longitudinal angles. So you can see up here they actually tell you what's what. They assert that phi goes from 0 to 2 pi, which we know is an azimuthal angle. theta goes from 0 to pi, which we know is that sort of longitudinal angle. I keep calling it the longitudinal angle. I guess what I mean is the latitudinal angle, right? It's the latitudinal angle, but it's definitely the angle off of the z-axis. So this is the angle around the z-axis. And then r, which is any positive real number, that means not 0, by the way, which of course would be a problem for this second term. So it's any positive real number, and t can be any real number, positive or negative, right? So this is going to be our time variable, our radius variable, and then our two angle variables. So we will be using that convention. We will be using that naming convention because the catalog uses it, and we're digging into a particular problem. So we're making those substitutions. X mu goes into these symbols here. So then this tells us, well, we know that we're looking for, we know the form is supposed to be G mu nu X mu X nu, right? X dot and X dot. We know that that's sort of the form of these elements, right? And so so we know that for G00, 0, I would need an X0, X0 here. And so that's what that is. So that we know that that is the G00 term. Likewise, we know that this is the G11 term. And then we also know that R squared is the G22 term, and then R squared sine squared theta will be the G33 term. And because everything comes in as its own little square, you know that there are no off-diagonal elements. There's no term like dt dr or dt d phi, right? And some metrics, of course, have off-diagonal elements, but this one does not. It's a diagonal metric, which is nice because the inverse, G00 is going to be 1 over G00 because of its diagonal nature. So that's nice. Let's see. So we now know the metric coefficients. So the metric components. So we'll start by studying that. But this chart, this catalog gives us more. It gives us the Christoffel symbols, which is nice. These Christoffel symbols, when you see the word Christoffel symbols, you are actually should be thinking metric connection. Metric connection. That is the metric connection. So in principle, once we know this, you and I can calculate these ourselves, right? We know the formula. But it's not like this is going to change a lot, so we will stick with so we'll do an example of it, but we will lean on their results here. And then the only other thing to talk about is their notation, right? They use this RS up here. And when you look up the Schwarzschild metric, very frequently you will see a different structure, a different form. So we'll break that down too. Okay, so let's begin by analyzing the metric components and calculate a few of these Christoffel symbols ourselves. All right, so when we break down our metric components, these are the only ones that survive, the diagonal ones. And a typical analysis of this problem will give you the 0, 0 component to be this expression here, the opposite of the quantity 1 minus 2m, which is a constant, over r, where r is the radial coordinate. So m will ultimately end up being the mass of the star that we're dealing with, but it shows up in the numerator of these things as 2m all the time, and that ends up being something called the Schwarzschild radius. Remember, in the units we're using, G equals C equals 1, mass is in units of length, right? So this numerator here, even though it is a mass, it's in units of length. So this is actually unitless, and in fact this whole thing here ends up being unitless. Same is true here. So that's very important to remember. In our units, which G equals C equals 1, mass equals length. So, we discussed this in one of our earlier lectures here. So this combination of mass, 2 times the mass, shows up so often that we give it its own symbol, alpha. Now the catalog, right, if you go back to the catalog, The catalog gives it a symbol R sub s, and that stands for the Schwarzschild radius, which is a very important feature of this spacetime. The problem is I don't want to run around writing a subscript on R. R itself is hard for me to write, and a subscript is even worse, and so I'm giving it the name alpha. Then, so you'll see, so whenever you see alpha, it's 2m, and it's a unit of length that characterizes the whole problem. In fact, this entire spacetime, the characteristic length, the length that sort of defines the entire situation, is this length 2m. So ultimately, I think we'll be measuring everything in units of the Schwarzschild radius, because it's the only length in sight, right? The radial distance is just an arbitrary number, but this is a specific value of a length, and it's the only one that shows up in this entire problem. So it's an important length, and we're going to call it alpha. The other change that we're going to make is this r. I've already said, r sub s. We're not going to do that. But when we think of spherical coordinates, right, we know that there's a radius, and we know the radius comes from the center, and it's a distance to some point at some radial distance away. The problem is in the Schwarzschild spacetime, the notion of radial distance involves integrating this thing along a radial segment of our problem, and it's not, that radial distance is not going to equal r. So this is really sort of a different coordinate than the simple radial distance we know from standard mechanics, from standard science, or standard mathematics of spherical coordinate systems. So I don't want to confuse that. So I like to switch the radial coordinates name from r to rho, sort of the Greek r, because that tells us we're dealing with the Schwarzschild coordinate system, and the distances, the radial distances, are not just going to be rho. And you might tend to fall back and think of it if you do r. Also, r looks a little bit like my n's, and so it's a little harder for me to write. So these are going to be our metric coefficients for the Schwarzschild spacetime, and those are the ones we are going to use. So we'll begin by going back to our expression for the metric connection in terms of the metric. Now, obviously, these are metric components here, and this sign here is telling us we're taking the derivatives with respect to this index, and this is the inverse metric up in front. And so the thetas will all sum out, and you'll be left with a beta up top and a mu nu in the lower index slots. So we're going to use this to calculate each metric coefficient, which will be a function of spacetime, right? Remember, these are functions of spacetime. That's why you're able to take their derivatives, and this will end up being a function of spacetime. So let's start with gamma 0, 0, 0. So beta equals 0, mu and nu equals 0. So everything except sigma equals 0. So we have 1/2 g 0 sigma times g sigma 0, 0 plus g sigma 0, 0 minus g mu nu sigma. Now here I've rewritten it in the notation that we're going to follow, where the 0 coordinate is actually the t coordinate. Now you can kind of see we're going to take derivatives with respect to the time coordinate, right? Instead of like the mu superscript, the 0 superscript of the coordinate system. So that would be versus, this would be the derivative with respect to x0, right? And this is the derivative with respect to the t coordinate. Same thing, but it's, like I said, it's, once you're digging into an example, you sort of stick with it. I mean, you go ahead and you allow yourself the freedom of being a little more specific and a little less general. So we look at this, and we see that these two guys are derivatives with respect to time, the time coordinate. But if we go back and we look at our matrix elements, of which there's only 4, right, we see that none of them are functions of time at all. So these guys are immediately 0. And even if they weren't 0, the only one we would need to consider is the ones with that are GTT with respect to t, right? Which is actually, which goes to right here. So we now, so all values of sigma, all the values of sigma in this sum and in that sum go away except for the GTT. And we definitely know that GTT, which is this guy, I guess I could write GTT, G rho rho, G, oops, G theta theta, that's going to be a mess, and G phi phi. Let me theta theta. So these guys are immediately 0, which leaves us this cat. So the only one that will, well, we've already established that. So now, ultimately, the term that survives is going to be 1/2 g t sigma g t t derivative with respect to sigma. Now, if we look at GTT, we see that it's only a function of rho, right? Only rho. So you can take derivatives of this all day long, but unless you're taking a derivative with respect to rho, you're going to get 0. So that means that theta has to be 0, which means it's going to be 1/2, or theta has to be 1. 1/2 g t rho g t t rho. Now this is non-zero. The problem is remember, g is diagonal, right? It's totally diagonal. Therefore, this term is equal to 0, right? That's going to now equal 0. So everything equals 0. So we now know that g t t t equals 0. All right, so we'll take that and move that aside. We've just figured out one of these things is equal to 0. And let's look at a different one. Let's now look at, obviously a lot of things are going to be 0 given the strict rules of all this, but let's look at one that actually isn't 0. T rho, right? T rho is not going to be 0. So we have 1/2 g. Now our beta comes in at t. We still have to sum over sigma, and we're calling g sigma, we're calling mu rho, and nu rho, and mu is t, and then g sigma mu is t rho minus g mu is t rho sigma. All right, so let's think about this a little bit. This first term, which is summing over sigma, this guy will only be non-zero when sigma equals rho, because our metric is diagonal. But when sigma equals rho, this guy is off diagonal. So this term will always be 0. So this term is always 0. Then this guy, when sigma is t, then it's non-zero, and when sigma is t, that's non-zero. So this one has a fighting chance. And we also know that the 0 term, or the tt term, is in fact a function of rho. So that one will survive. So this one will survive, and it will survive in the form as 1/2 g t t times g t t rho. All right, so how about this last term? It will, well, it's already a fail, because the only thing it changes is sigma, and this is non-diagonal. This is t rho, so that guy's 0 right away. So we're left with this cat. So what is it? So I will make the substitution, which I just did. I substituted for this, which is the reciprocal of 1 minus alpha over rho, and there's the -1. So this is the, I've taken this -1 factor and I'm pulling it out as a very obvious -1. But this guy, the inverse of these, of of this is simply the reciprocals, because you're dealing with diagonal condition, right? So because it's diagonal, we're very lucky because we can easily calculate GTT is 1 over GTT for the diagonal metrics. And if you're curious about that, just work it out. G alpha beta times G beta gamma, when you have only diagonal terms, if that's going to be 1 everywhere, you'll see that that's the case. So let me erase this. So this term here is the reciprocal of that guy, and now I need to take the row derivative of GTT, so it's the row derivative of that. And this is that calculation. So we're taking this derivative, that gives you alpha over rho squared, right? The negative sign cancels that. Of course, the derivative of the constant term is 0. So you lose a negative sign there. This negative sign and that negative sign combine to cancel, so you have the 1/2 out in front. So you end up with this divided by that, which is ultimately alpha over rho squared minus alpha rho. Pull out an alpha and you get alpha over 2 rho minus alpha. So ultimately that is our answer for this one, where we write, let's go back to black. Gamma t rho equals alpha over 2 rho minus alpha. Okay, and what's obviously interesting here is, you might as well just start seeing, when I say that alpha is sort of a standard of size of the problem, it's the only size in sight, it's the only number that actually has physical significance. You see that when the radius approaches this distance, this blows up. This becomes very, very big, and that, of course, is a significant issue with this whole coordinate system. But anyway, so we've now calculated one non-zero connection coefficient. So I'll put that over here. Well, I guess we should check the catalog, right? See if we got it right. Let's see what we have here. We calculated this one, and there it is, alpha 2r minus alpha. So that we've just calculated that one. Actually, this tells us all the ones that are non-zero, so we can kind of waste. So you see that in principle there should be 4 times 4 times 4. There should be 16 times 4 different connection coefficients. Now that's reduced a lot by the symmetry of the metric, but in non-zero connection coefficients, there should be 4 times 4 is 16. 16 times 4, 6 times 64. And there should be 64 of these, but because of all of those things that we just saw, most of them are not. Most of them are 0. But these are the ones that are not 0. So let's look at for another interesting one. Which one is interesting? That's kind of interesting. That's this one's interesting. I like cotangents. So let's calculate this one. Phi theta phi. All right. So here I've written out the metric connection formula for phi theta phi, and we'll use the same technique, right? The same technique will be, the only time that this cannot be 0 is when sigma equals phi, but sigma and phi here match, so that one's actually going to be good for that one circumstance. So that guy will have a non-zero value. It'll have a non-zero value as long as this is a function of theta, but sure enough, this is phi, and it is a function of theta, so that's good. What about the next one? This one will only be good when sigma is theta, but if sigma is theta, then this guy is 0. So that guy goes to 0. That's gone. And this one is never good because it's mixed to begin with. It had no hope of survival even from the start. So this is the total value of this connection coefficient. Then we just make our substitutions from this formula right here, right? That formula right there, and exploiting the fact that the inverse of a diagonal metric is just the reciprocal. That throws it throws the metric component into the denominator. And now we just have to take the derivative with respect to theta of this, which is quite simple. And that's clearly just a combination, just a little chain rule exercise. And the rows are going to cancel, one factor of the sine is going to cancel, and the 2 is going to cancel. That's going to leave us with cosine theta over sine theta. And I happen to know that sine over cosine is the tangent, and cosine over sine is the cotangent. And so that is the value of psi theta, phi theta psi, or phi theta phi. And we should just check the catalog entry. I mean, we picked it because it was kind of cool, but there it is right there, and we got that one right. Okay, so we can do this for every one of these things. The point is I want to make sure at this point that you're looking at the catalog and you're saying, oh, okay, well, there's the metric coefficient, or the metric components. I can extract the metric components from this piece of the catalog, and I can calculate each one of these because this is the metric connection, and I know the doggone formula for the metric connection, which was not easy to derive. I thought that was a pretty tricky formula to derive. We derived it abstractly, which was actually very hard. And then we derived it through the variational principle, which was a lot easier, actually, I think. But I like the abstract method, too. I like them both. I find them both very stimulating in different ways. But this, using this formula, we can derive this. So the whole thing is this should be less of a mystery, right? And now the partial derivatives of this, we'll see that those are necessary later when we take second derivatives of things to calculate the Riemann tensor. So now you're just taking derivatives of the things we just took a derivative of. So for example, this guy, it's a function of theta. So I should be able to find a comma theta version of that. And there it is, right? And sure enough, I mean, that's not too hard. You just take the derivative of this with respect to theta and you end up with that. So if you need the derivatives, the partial derivatives, the ordinary partial derivatives, because notice he uses commas here. So I would have written this as gamma phi theta phi single line theta, which would be the partial derivative with respect to theta of gamma phi theta phi, right? That's what that would have been. So there's no mystery. This whole first section of this space-time has been demystified, I suppose. Okay, so now we're going to allow ourselves to presume that we know the Christoffel symbols, right? We've calculated 2, so we're confident we can calculate them all. And now that we know the Christoffel symbols are what they are, we can now execute the geodesic equation. So that's our next step. And here is our starting point. This is the geodesic equation. We know that x, because of the way it's structured, you know that we're solving for a path in space-time. So by now you should realize that that path is given as a function x mu of lambda. Lambda is some parameter, and the time along that path will be x0 of lambda. The first coordinate along that path will be x1 of lambda, etc., etc., etc. So you now know, just by looking at the geodesic equation, it's a differential equation, right? So it's got to be solved for a function. But there's 4 differential equations, one for each beta, because remember the mu's and the nu's sum out. So you're only left with beta. So you have 4 of these guys. And that doesn't mean you're solving for 4 different paths. That means you have 4 coupled equations that have to be simultaneously solved by the same function, x mu of lambda. Just a little refresher on differential equations a bit. But the only mystery here is this guy, which we now know the answer to because we were given the metric, right? We were given a metric, and therefore we know what this is. And we just sort of exercise that. So now let us actually write down the geodesic equation for the 0 component, or the time component. Right? So we're actually going to change this now. We're going to make this look like this. And you can kind of see how confusing this might get. I want to do the first one where beta equals 0. So I substitute that, and I say, well, wait a minute, in my system, x0, that's the time coordinate. So I'm going to use this little t instead. But, so when I substitute the little t, I can do it here just fine, and I can substitute that t here. Now it's no longer an index. It's actually, it refers to a specific coordinate. It's like I had replaced beta with 0, but instead I'm replacing all those zeros with a t. But I still got a sum over mu and nu, so I kind of have to leave the x form here to imply the sum, because x0 still is t, x1 is theta. I can't replace that with t with a superscript. That's ridiculous. T is a name of a coordinate. So I have to leave this sort of open identifier for the coordinates to finish up this side, just so I can capture the sum. But let's just break the sum out and get rid of this confusing mixed notation. All right, so to do that, what do I need? Well, I need to find the non-zero values of the connection coefficient where the superscripted index is time. And I can go back to the catalog, and I can look for that. That one has a superscripted index of r. Maybe I should blow this up a bit. This one has a superscripted index of r, so that doesn't help me. Theta, so none of these help me. Here's one. That has a superscript index of t, so I know that this one's non-zero, so I have to make sure I have that. These two don't help me, and none of these two. This is the only one. This is the only I'm surprised. This is the only connection coefficient that actually survives, because it's the only one where the superscript is t and the subscripts will sum over everything, but only one term will survive, and that's the TTR term. So if I go back here, I now know that the only surviving term is going to be the TTR term. So I might as well just write that down before I forget it. TTR. So all the rest will be 0, so this is going to end up being mu is t, so it'll be dt d lambda, and dr d lambda will equal 0. And then I guess I push d squared t over d lambda squared. So this is the first geodesic equation. Well, actually, I guess I should write it out. Okay, yeah, this is the first geodesic equation where I actually substituted for this. So now we see that this is a geodesic equation, and there's two of the 4 functions are involved. Ultimately, it'd be t of lambda and r of lambda. So if we knew t of lambda and r of lambda, and we substituted those 2 functions into this equation, we better get 0. Lambda will be forced to be an affine parameter, by the way, because of the geodesic equation we chose forces it to be affine because of the 0 over here. So there it is. That's your first geodesic equation that we've solved. That's pretty cool. But there's 3 others, right? There's one for r, theta, and phi. So let's work on those. And here we have it for the row equation. Here I've expressed the general equation of the general geodesic equation is here. Now I'm going to take beta and set beta equal to 1. So if beta equals 1, then x1 equals rho. Then we get this guy. And I'm switching up the notations a little bit, where this is obviously d rho squared d lambda squared, right? So that's the second derivative with respect to lambda, and these guys here are first derivatives with respect to lambda, these x's here. So now I need to hunt down the connection coefficients that are non-zero for this circumstance. So I'm looking for connection coefficients where they have a row up top and we have a non-zero connection coefficient. So let's go back and look for those. And the ones that have a what we're calling a row on top is this one here, and this one here, ooh, and this one here, and this one here. So there are actually 4 of those guys. So we better get to work. So here I have assembled the geodesic equation in symbolic terms. What will happen is, so this, for example, this connection coefficient, rho tt, will go here, rho tt. Mu and nu will both be t, so you'll get t dot times t dot, which will be t dot squared, right? So that's so there's the function out there that solves this geodesic equation is t of lambda, and then dt of lambda with respect to lambda equals t dot, and we're actually asking for that function squared right there. So and that's true for all of these, right? Each of these is the same. It turns out it's just tt, rho, theta, theta, and psi, which are non-zero. And in each case, because these two indices are the same, you end up with the square of the corresponding function here. So this one has all 4 of the functions we're seeking in it. We're seeking, what we're seeking ultimately from this equation here is we're seeking x mu of lambda, which is x0 of lambda, which is the same as t of lambda. It's x1 of lambda, which is the same as rho of lambda. So that's what this means. It's important to keep in mind what the solution of the differential equation is all about, and that's why I keep stressing that. I know I've said it a few times already. But the stuff gets pretty messy, and going back and reminding ourselves, okay, this is how it works. But this is reminding ourselves what we're looking for, what the differential equations solve, sort of what our goal is. But now we have to make the substitutions for these guys. So let's do that. All right, and here is that substitution, which gives us our second geodesic equation. So we have, now this is a geodesic equation. Well, it's all coupled, right? I want to say it's a geodesic equation for rho. It's the rho geodesic equation, right? Because beta was set to 1, which is our radial variable. But clearly, I mean, you need to know all of the 4 geodesic expressions to get it. I mean, you would need to know all 4 mu's to get this one. And the coefficients are actually, I mean, rho appears as a second derivative there, as a function here and here. Its first derivative is squared, so clearly this is nonlinear, right? This is a nonlinear differential equation, and this one too. Let's see. This is a couple differential equation as well. So this differential equation is our 0th. This is our 1th, which is our rho. So we have 2 more to hunt down. So here is our next one, where we set beta equals to 2, which and x of 2 we've identified with the latitudinal variable, if you will. So now we have to do the same process. We have to figure out which of these exist, which of these are non-zero with a theta up there. So we go back to our catalog, and I see one here. So let me first get rid of the, and we see this guy here is non-zero. That's good. And this guy here is non-zero. So this was going to be a little simpler than the last one. We're only going to have 2 thetas that survive. When we substitute those into the problem, I've put the rho theta one here and the phi one there, and then this one is multiplied by, this is the first, I think this may be the first mixed one we've actually had, right? These were all the same, and this one was mixed, right? So this is t dot r dot. Actually, that r should be a rho, right? So this expression is similar to the first, and now we need to just substitute in the actual values for these guys. You know, I just noticed something. Look at this. If you look at that, you realize that mu will sum with that. We know that this is symmetric in these two indices. So when I look back at this, I have to remember that gamma theta r theta equals gamma theta theta r. So because of that, there's actually two of these that are, whenever the index is mixed, we end up getting the term twice, which means when I go back to my first geodesic equation, when I work with this term right here, right, TR, I should also get an RT. But it's going to be the exact same thing. These two are going to be switched, but it's going to be the exact same thing. So I have a factor of 2 here, which eliminates this 2 down here. So that 2 doesn't belong. So I'm going to erase that 2. All right? So that's an important point. I overlooked it. I just realized it as I was calculating this guy, right, is that we're going to get a factor of 2 right here because these are symmetric, and the catalog even says as much. Easy mistake to make. By the way, it doesn't affect anything here, right? Because these have no mixed indices. So this equation is solid. It's this one that, and the one we did before that I'm off by a factor of 2 in that first term. Anyway, so let's finish writing this guy out. And there you have it. That is the third geodesic equation. And then we have one left. And here it is, right? The standard, the general geodesic equation, we set beta equal to 3, and x3 corresponds to phi, which gives us this guy. So now we have to hunt down these guys that are non-zero. And looking here, let me erase the previous ones. Looking here, what I see is this one is non-zero. This one is non-zero. Is that it? That doesn't count. That's zeros. That's bad. That's bad. Okay, so just 2, the cotangent one and the 1 over r, 1 over rho. Okay, so with those 2, we can now make our substitutions. Let's see. We have theta, phi, and rho phi. And here's our final geodesic equation right here. Our final equation. I'm not forgetting my factors of 2 again, and so now we have all 4. We have all 4. In fact, I will summarize them. And here are all 4 of them. They are the t equation, which I left in the form where you explicitly see the derivatives. Then I started using the dot form. This is we would call this the rho equation, the theta equation, and the phi equation. But obviously, all of these equations are completely coupled and horribly nonlinear, right? I mean, this is I mean, just quite a huge nonlinear mess, right? These guys are totally nonlinear. The highest degree seems to only come in the first order, so that or to the first power, so that's nice. But these guys have got to be solved, right? We cannot know the path in space-time in a Schwarzschild system until we solve these 4 coupled equations, and it's not trivial to do. But we will work on solving these guys in the next few slides. Now, I got to say, solving these equations is a little different from understanding general relativity. Now you're kind of doing an exercise in practical mathematics, and I'm fine with that. So I'm going to take a few. I mean, in fact, the book that I wrote and have provided to some of the Patreon members, Why Does It Move? Basically, half of that book, at least, is just the practical mathematics of solving these equations. And of course, there are certain simplifications we can make. For example, by understanding the symmetry of the whole point is this is a completely physically speaking, this is a completely spherically symmetric problem. So we can make some simplifications by choosing theta to be fixed, and that'll eliminate a lot of offending terms, right? If we choose theta, say, to be, say, 0 or something. We can eliminate this term and eliminate that term, and so it simplifies quite rapidly. But it's going to take a lot of work to crunch through it, and in the end, we're going to have some integrals that are quite challenging. I don't know how far we'll actually take this, but I do want to make it so you feel like you have solved a geodesic equation that's not a straight line in Minkowski space. Okay, so we'll continue this work next time.